Hi everyone, this is the continuation of deadlock avoidance. In this deadlock avoidance, now we are going to see the algorithms based on the instance of resources. If the resource is of single instance, then the RAG, which is of resource allocation graph, is used for deadlock avoidance. And the resource type is of multiple instance, then we will be using Banker's algorithm for deadlock avoidance. In this, the resource allocation graph algorithm is seen first. In this, the claim edge is nothing but the request edge from Pi to Pj indicates Pj may request for resource Rj represented by a dashed line. Okay, in this, claim edge is nothing but an request edge, and dashed line is indicates the request path which can be granted. For example, let's see here. Here is the dashed line indicated, right? In this, there is a dashed line from P1 to R2 and P2 to R2. This represents the resource R2 might be requested by the process P1 and P2, and it might be changed. The request edge can be changed into an allocated edge from R2 to P2. That is indicated as dashed line. Dashed line is nothing but currently there is no request or claim edge or assignment edge is in between that resource and the process, but in the further execution of that system, that dashed line is a pathway which can be converted to an request edge or assignment edge. Okay, in this, the claim edge converts to an request edge when a process requests a resource, and the request edge converts to an assignment edge when the resource is getting allocated for the process. When a resource is released by the process, the assignment edge is reconverted into an claim edge. Okay, the resource must be claimed as prior in the system, that is before the system is getting entered into its execution, it must hold all its resources, right? So all the resources must be claimed priorly in the system. This is the resource allocation graph. In this, we conclude that the resource R1 is holded by the process P2, and the resource R1 is holded by the process P1, whereas the process P2 is requesting for the same resource R1. In further, the process P1 and P2 can request for the resource R2 also. Here, this is the representation of unsafe state of the resource allocation graph. While allocating resource to the process, we must ensure that there is no formation of this cycle. In this, from P1 and P2, the resource R2 is having only a claim edge. It can be either converted to an request edge or the assignment edge. We must ensure that before assigning that resource to the process, no cycle is getting formed. In this given diagram, the cycle is getting formed. For example, let's see here. The resource R1 is held by the P1, and P1 is requesting for R2, whereas R2 is held by P2 and P2 is requesting for R1. So a continuous loop is getting formed. If a loop is getting occurred in the RAG, then there is an occurrence of deadlock. So we must ensure before allocating the resource, we must check there is no formation of cycle in that resource allocation graph. And that is only explained here. Suppose the process Pi is requesting for a resource Rj, the request can be granted only if converting the request edge into assignment edge does not result in formation of a cycle in the resource allocation graph. If the cycle is getting formed, then there is a possibility of occurrence of deadlock. So before allocation, we must ensure no cycle is getting formed. Then that RAG is for single instance of resources. For multiple instance of resources, Banker's algorithm is getting used. In this, each process must have an prior claim edge which is getting used, and the process request resources may have to wait because the already resource instance are getting allocated for another process. It must wait for its time on the waiting queue, and after releasing of that resource, it can be utilized by the requested process. When a process gets all its resources, it must return them in a finite amount of time after completing the execution of that process. That was explained in Banker's algorithm. The Banker's algorithm consists of available, maximum, allocation and need. Available matrix is consist of the resource which is getting allocated already to the process, and maximum is nothing but the number of instances which the process needs for execution to its maximum, and allocation is nothing but how many resources are currently being allocated for that process, and need is nothing but how many resources are further needed for by that process for its execution. That is nothing but need is nothing but maximum minus allocation is the need matrix. Here this is the safety algorithm which we are following for ensuring the system will not enter into an deadlock state using Banker's algorithm. If you follow these steps one by one, then the system will get avoided by entering into the deadlock state. Let us see the execution and flow of this algorithm by using an example numerical problem. It will be much more effective for better understanding of Banker's algorithm.